everyone, it is time to do some office hours. I see there's a question right here about Data Analytics 5. Yeah, Claire and Lane have questions about that. Gotta clear my throat right there. Let's do that right there to start. Data Analytics 5, Stat 201, Data Analytics 5. Now, I want to point out we did a lot of questions about Data Analytics 5. Oh, cool. Okay, let's head over here to the main screen. Yesterday, we did some data analytics, so I'm going to pull up that video too and kind of link that, and we'll kind of do a little bit of, I guess, cleanup right here. I want to check one thing, though. Did I ask you to make a residual plot? Did it ask the residual plot? Let's go over here to assignments and see if it asked about the residual plot. But ask those questions. Let me know what you're thinking. Data analytics, number 5, regression right here. Can I not? New tab? Yeah, new tab. What are people? It did ask you to make a, well, residual. Let me see. Residual plot. Residual? Oh, it does say the residual plot. Oh, okay, that's what I forgot yesterday. Yeah. Also creating the residual plots. Yeah, I didn't create a residual plot yesterday, so that is in the instructions right there. It does say create the residuals by plot. And see down here, report the see, I looked at those. It does say create a residual plot, so I didn't do that yesterday, and always read the instructions. It's not that hard to create a residual plot, though, so let's make sure people see this, and then I'll make sure both of these are in the... We're going to have people in other classes, though, who maybe are like, wait a minute, how do I create that residual plot? But we'll put it in this video right here. So we're going to show how to create a residual plot. Okay, so with this right here, I think we have everything now, because down here, correct output... Oh, so literally the only thing we missed was the residual plot. Only the first residual plot. Yes, that's the only thing we missed yesterday. No. Okay, let's try to get that. Rubik says, include all the output info under linear fit. Do we need to include the lack of fit stuff? No lack of fit is needed. It's not automatically given from a struct menu, so I don't know if we need to show it. Yep, that's got it right there. Here, we'll go ahead and do this right here. So let me pull up some data. I'm going to close out, see if I have... What do I got over here? I got regression solvers. Darn... Residual plot. It's good to get a residual plot. Let me get some data open for you right here. So when we do a residual plot, I know you can't see my screen yet. Where's my student data? Here we go. Okay, let's put the new section in the video here. Required output for the visualization. So very clearly, I'm going to resection this video. Required output. Okay. Required output. Okay. So when we do a regression requires what? Very clearly, regression requires what? So these are the easy questions. Regression requires we get what here? So these are the easy questions. Like, let's throw some points to the chat. So regression requires what? What do we need for regression? To do regression, we are required to have what? To do linear regression. There are other types of regression, which I won't mention here. But to do linear regression, QQ, 2 quantitative variables. Great job right there, Claire and Lane. QQ, 2 quantitative variables. So we go here to analyze fit y by x. Analyze fit y by x. And when we do fit y by x, this is a bivariate relationship we're going to do right here. So we're going to have the y variable of interest, and the x variable is going to be the explanatory variable. Interestingly enough, you can go right here and eliminate the character and also eliminate expressions. We don't have any of those, but now we only have quantitative numeric variables. Everything blue right here means quantitative. I don't know why weekly text doesn't have a little dash. The numbers are just question 15 on the survey, and then there's the name of the question. So if we wanted to see if the number of pets someone owns can explain, you see how it's the X variable, does number of pets you own explain how much you spend on pets? So we're asking, does your pet numbers, how many pets you own, explain why you spend so much on pets? Good way to kind of talk through it right there and be like, okay, this is the response, the thing we're talking about up there. It is the explanatory, also known as the predictor. I don't really like that terminology for it. I like to say it explains why, explains X, but it is the predictor, and the top one is the predicted. So words for the Y variable are the predicted, the dependent, mathematically speaking, also the response. I call it response. You can flip-flop. You could say how much people spend on pets explains how many pets they own. Sometimes it makes more sense to go a certain way, like maybe you might say, you can do other things, like how many hours you're taking this semester, does that explain how much you read? So you think about, does your credit hours during this semester explain how much you are reading each week? So maybe it does. Maybe there's a relationship there. But we'll look at pet expense explaining how many pets you own, or no number of pets. Like, does how many pets you own explain how much you spend on your pets? Like you said, it could go the other way. And here we go. Click OK. Now this is a scatter plot, and this one has a lot of issues. Like, this is not the bestest scatter plot. We're going to go ahead right here after we make the scatter plot and go to the red arrow. We're just talking about how to make the output right now, not really interpreting it. But we're going to go right here to the red arrow and go to fit line. That's going to add the line of best fit. The line of best fit tries to get as close as it can to every single point. Hence, this is linear regression. So when we hit the fit line, it adds the line to the output, and you can really see the issues. The very clear issue with this plot is what? I mean, it might have some straight enough issues, but there's a very, very clear issue with this. Very, very clear issue with this. Very, very clear issue with this. Outliers. Tons of outliers. You can, if you want, this is not required, grab the points that are outliers and go to rows. And this is not required, but it's what we generally do when we try to make things look all pretty. And we go right here and we put them red right there. Go to rows again, and we still have them selected. Go to markers, add a little marker, and there's those outliers there. We highlight these points I'm just grabbing. This is not required. It just makes things look pretty if you want. Go to colors and go right there. We can actually color these different because these points actually have what residuals. Those points have very what residuals. Let's color them a blue. Those points have very what residuals right there. Kind of learning some topics right here as we're reviewing this. These points, the blue points, have very what residuals. So we're kind of reviewing right now, making sure we know the topics. The blue points have the what are residuals. So what are the blue points? I don't know if it's really plot thickening. Looks to be more the outlier issue. But the blue points have what residuals? You could comment, make sure we talk about the QQ straight enough. No outliers, plot doesn't thicken. Yesterday's video covers that really well and give the details on it. This one, I would really probably just be talking about the outliers here. I would say for this plot, it is 2 quantitative variables, numbers, pet, and pet expense. I want to be careful because I don't want people to write exactly what I write. I want you to think about what the conditions mean of 2 quantitative variables. Does a straight line well describe the relationship? Also, are there outliers? We do not want them, and the plot doesn't thicken. But what about these blue points right here? We're going to show the required output here in a second. What's different between the red points and the blue points? Like what is characteristically different that the red points have this and the blue points have this? So the blue points are where? They are a little closer. They're under the line. So what does it mean if you're under the line? If this is the observation, which is how much someone spends, if we trace over to the left, they spent $2,000. So if you were to trace over here, they spend $2,000, but they're expected to spend about $4,000 or maybe even $5,000. That means they have a what? So think about this. This person right here spent $2,000. They were expected to spend about $5,000 according to the model. So what am I trying to point to right here? So the predicted is higher than the, well, so less than expected. So they have a negative what? Being below the line right here means you have a negative what? And these are keywords to know and understand that this point right here has a negative what? And we'll see this in a moment when we make the plot of them. But this point right here has a negative what? Like if this is 5,000, like I'm pretending it hits right over here at 5,000, negative residual. Great job, Jesse, right there. So what would its residual be if it was predicted to be 5,000, but it's actually 2,000? What would its residual be? If it was predicted to be 5,000, that's where it hits the line, we'll say. Or like there, the line is at 5,000, but it actually is at 2,000. So what is its residual? What is its residual? Negative 3,000. Now these points up here, this person spends 20,000, but they were probably predicted to spend around 2,000. So what is this person who is predicted to spend around 2,000, but actually spends 20,000? What is their residual? They were predicted, let's say 2,000. That's where the line is for them, but they actually spend 20,000. What is that red point up here's residual? 18,000, which means they're 18,000 above their prediction. So the residual is how much you miss by. And what's really great is we can actually see the answers to what we were just trying to solve by going here to the red arrow under the linear fit, and you need this output, and go to plot residuals. Where's that plot residuals? There it is right here. So here's the plot of the residuals. And you remember how we estimated this person right here? They actually have a residual closer to 20,000. Wow. So, oh wait, we want this one. Whoops, wrong one. There we go. Here is the one that you want right here. I grabbed the wrong residual plot. It's the first one we want. And take a look. Remember this person? We said that their residual, well, tell me it, darn it. We were trying to figure out what their residual was, and I wish we could see exactly, but we said about negative 2,000 or negative 3,000. And then the person up here, we said about 18,000, and you can see these are the residuals. Notice that the blue points are below the line, and the red points are above the line. Now, when you make a residual plot, what happens to the residual plot? It's going to close everything, isn't it? The residual plot, I knew it would do that. The residual plot is when you make the line what? A residual plot is when you make the line what? The residual plot we use is when you make that line, you see the blue line right here, horizontal, flat. So the residual plot literally tells you the vertical distance from the line. Like, see this point right here? It's the same point here. See this point over here on the far side of the plot? This point right over there? It's the same point over here. Frankly, if we stretch it out to the same degree, it might make even more sense that you're just seeing the same plot, and that's a histogram of the residuals, but this point over here is the same point there. This point right there, same point there. These points that are above the line, still here, and the blue line is the original red line, but flat. So a residual plot is going to give you a plot of all the residuals. Very handy. So let's talk about what we need when we do this. Well, a few things we're going to need right here is we're going to need the linear fit. Yours is probably going to look better than mine. I'm going to delete some decimals and make this look nice and neat right here. We don't need the Q numbers on this. So I'm going to put here pets right here and then change it to this. You can edit these. Don't change what they say, or don't change like the meaning, but there is the linear fit, also the model below it. So I would take a screenshot of this right here first. So what do we have right here? What is the top thing and what is the bottom thing? So we have what? Let's see what we have, and this should be one of your screenshots. So this is the first screenshot I would have right here. What is the first thing right here, and what is the second thing? So we should know what each of these things are. So when you look at them and interpret them, you're like, oh, that's a this for the this. What is that right there? Up top, thing number one is a what? What is the first thing? These are good review questions. They can appear on the test. Like a blank is the relationship between two blanks. Regression line in a scatter plot. Yep, because a scatter plot is the bivariate relationship between two quantitative variables, and then the addition of the regression line right here, and then the regression line equation, which is y hat equals b0 plus b1x, making this right here b0, the intercept, and this b1, and this x. And check out yesterday's video where we go into proper interpretations, but the more you practice them, the better you get. As in, someone who owns 0 pets would be expected to spend $342.6 on their pets. That is not very logical, but maybe they're spending it on other people's pets, because we would expect someone who owns 0 pets to not have a pet expense, but the model predicts that their predicted pet expense would be $342.6. Maybe a little bit illogical, I would comment. For each additional pet, we would expect somebody's pet expense to increase by $254.2, and that is the interpretation of the slope down there, B1. So knowing that this is the linear fit, which is the regression equation, you could always do things like this to make it make more sense if you want. Regression equation, and you can edit pretty much anything. That's why jump is pretty cool. Just making your output look nice and neat. And scatter plot of pet expense by number of pets owned. We want to make things look nice and neat right here. That's part of our goal. Nice and neat. And I'd probably re-screenshot now and include this. I wish that didn't wrap there though. And once again, you can always crop if you get too much. So that is your first screenshot. It doesn't have to look perfect, but that's going to be one of your best screenshots right there for the first part. The next thing we need right here is the summary of the fit. The summary of the fit shows things like the R squared. What does the R squared mean? Well, this is one of the values we need to know for the test. The R squared is the percent of variation in Y explained by the variation in X. What is R squared not? If you're watching this video right now, I wish I had flashing lights to appear. Or like a whamp, 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 whamp. R squared is not what? We talk about this in my class a lot because a very common mistake for the test. So R squared is not what? R squared is not correlation. Do not interpret it like correlation. It's the blank percent of the variation in y is explained by the variation in x. So let's take a pause right here. This is one of the more commonly missed questions on the test. But if you know how to interpret R squared, how would you interpret R squared here? I think I did it just a second ago. But think about what it means. And this output is the output you want right here. Don't need to highlight it. There were 806 observations. The mean of pet expense was 655. Root mean square is the typical miss the model makes. We don't interpret that. The only things you would need to know are probably those two. Mean of y is y bar, which is not bad to know either. The average of the y. What is R squared interpreted right here? Which the project doesn't, or the data analytics doesn't ask for, but it's on the test sometimes. What is R squared interpreted right there? A lot of people get this wrong. There's written questions on test 2, and a lot of people get this wrong. A lot of people says interpret R squared, and they say correlation. I'm like, no, it's not correlation. It's called the coefficient of determination, actually. So what is it? How do we interpret it? I'll give another 10 seconds here or so. I'll throw some points because people aren't answering questions. It is 13.6% of the variation in pet expense is explained by the variation in number of pets owned. Blank percent of the variation in y is explained by the variation in x. So you fill in the blanks. Make sure it times up by 100, though. Blank percent of the variation in y is explained by the variation in x. So 13.6% of the variation in pet expense is explained by the variation in number of pets owned. Blank percent of the variation in y is explained by the variation in x. And don't use R squared adjusted. That's a different concept for 320. It's R squared adjusted for the multiple world. The last thing I would say to take before we get the residual plot down here is the parameter estimates. Can't edit that table. I can. The parameter estimates are very important, especially to know for the test. When you have the parameter estimates right here, this value is the estimate of the what right here. Think about what that means as it points in on it. This value is the estimate of the what. So this is another screenshot I would take right here. I would take a screenshot of the parameter estimates. That is an estimate of the what. Like connect in the dots to be like, that is an estimate of the what. What is that value right there? That is an estimate of the what, which you can actually look up here and see it right there. That is the estimate of the what, making it B0 in notation. It is B0, correct. That is B0. That is the estimate of the intercept. That's the notation for it. So B0 is when x is equal to 0. We expect y to equal B0. Then the other value right here is the estimate, and it has the x variable name, making it the estimate of the slope coefficient. That's the name of the x variable right there. So that is B1, the estimate. And if you look right here, you can see it in the above output. Look above it over here, and you can see 254.2. And that is the estimate of the slope coefficient. Now, very importantly, we care about the slope not being 0. So that is the significance of the linear model. Because if the intercept is 0, well, the intercept could be 0, and we have a slope. And that's a significant relationship where x and y have some sort of relationship. We're pretending that it is statistically significant, because the least significant relationship would be a flat line. But the intercept could be equal to something like 20. And it doesn't matter if the intercept is equal to 0. We care about the slope not being equal to 0. Maybe the slope is equal to 2 here, but over here, the slope is equal to 0. So if the slope is equal to 0, that is the least significant relationship possible. We care about the statistical significance of the slope. This other p-value up here doesn't really matter. I mean, it tells you that we have good reason to believe that the intercept is not 0, but the intercept is not the xy relationship. The xy relationship is governed by the x variable. Last but not least, we need a picture of the residual plot. And it is the first residual plotter here, and this is the one thing I missed yesterday. So don't miss it. Don't miss this one picture. And that'll do it. There's the last picture. I think it's got everything. There's all the pictures you need. Also, we kind of went through all the output again. Really, this plot has more of a problem with outliers. You see the extreme residuals on the left side, and which are very high, and then the extreme residuals on the right side, which are very low. There might be issues with linearity, but the big problems I see right here, I don't really see plot thickening, because the plot thickening is about the same throughout. It's more of a problem of the residuals that are too low and the residuals that are too high. The linear fit, there is a way to technically check that. is a problem. Don't include the lack of fit or ANOVA. Yeah, the ANOVA and lack of fit are different things. What's interesting is you can actually take, that's a ridiculous value, a lot of variation. You can take the amount of sums of squares we reduce right here, and watch this. This is a fun trick. I'm going to solve this in my head. That's about 0.135898. Oh, look at that. I got it right. So the ANOVA shows you the reduction in the sums of squared error over the total error that exists from the naive model. And that reduction right there out of the total is R squared. So that's how R squared is actually calculated. And then the F ratio, another fun fact. These are fun facts. Don't write these down. Fun fact about the F ratio right there. If you take 22.60892 and square that, you will get the F ratio of 1. No, wait a minute. Oh, no, it's the T ratio. What have I done? The T ratio of 11.24 and square it. There we go. Those are just random fun facts. There's that. And if we had more decimals, it would be accurate. But do not include the analysis of variance. Do not include the lack of fit. That's to see if the linear model is a good fit. It's kind of like a fit for the normal curve, but you want screenshot number 1. Here, I'll review again. Screenshot 1 right here. That include the model. There you go. Good info right there. Cover that in the class. Screenshot 1 right there. Screenshot 2 right here. Screenshot. I would take different screenshots so you can make it look nice and neat. Screenshot 3. And last but not least, screenshot 4. There we go. Yep. Good stuff. Any other questions right now? What are people thinking? Let me know. Those are the screenshots we need to get the great grade. And I think that covers everything we've went through here and covered the important parts of it. I was confused on logical when it comes to the index or the intercept. Well, an intercept of 0. Well, so I can't fully interpret yours because I don't want to go away answers, but you have to read it aloud and think if it makes sense. So when I look at this right here, there are some that don't make sense. Like if we are predicting, let's think about interpret the intercept here. You ready? Interpret the value of the intercept here. First off, what is the intercept? What is the intercept? What is the intercept? So when you interpret the intercept, you have to see, yep, and I rounded it. So what does that mean? Interpret it and then tell me if it's logical or illogical. And I'll show you it over here. I wouldn't move your plot this far back if the data doesn't show it. This is just for teaching purposes because we don't usually graph where the data doesn't exist. This would be what is called an extrapolation of your model. When you leave the X bounds of your model and make predictions all the way back here, you're extrapolating your model well beyond the data. So what does the interpretation mean? It would be when X is equal to 0, we expect Y to equal B0. When X is equal to 0, we expect Y to equal B0. So when X is equal to 0, we expect Y to equal B0. And you can see it by just plugging in 0 for that and then solving the equation right there. So what is the interpretation of it? What would be the interpretation of this? When age is 0 years, we expect high school GPA to be equal to 5.92, right? So when age is equal to 0, we expect high school GPA. So does that make sense? Does that make sense? And you could add on average. I think they shouldn't want on average on that. Why doesn't that make sense? Like, why is that illogical? So this is where you have to be like, well, that doesn't make sense because... Does it make sense? Does it not make sense? When age is equal to 0, we expect the high school GPA to be equal to 5.92. So does it make sense? Does it not make sense? What would you say? Like if someone said, when someone's age is equal to 0, I expect their high school GPA to be equal to 5.92. Well, you can kind of be 0. It means you're what? Yeah, and that's right there. Jesse right there has a great answer. Jesse said you're not in high school at age 0, which is like when you're born, and GPA does not go up to 5.92. So really, we're outside the bounds where high schoolers are people, age of high schoolers. We're also outside the bounds of high school GPAs. Maybe you could be like, but what if it's like an honor system with AP? You could say, well, even then, the age of 0 doesn't really make sense. So that's how we would explain logical or illogical. A lot of people just say, yeah, it's logical, or yeah, it's not illogical. But you want to give sound reasoning and walk someone through and be like, well, people aren't in high school when they're a newborn baby. And then also, high school GPA really doesn't go that high. Even then, GPA only goes up to 5. Hey, Taylor, good to see you here. So, yeah, give that reasoning there. Be like, really, the maximum GPA we ever see is like 5. This is well beyond the bounds. So, yeah, that's the kind of reasoning we want when it comes to, is it logical or is it not logical? Like, make sure to explain it that way. Sometimes people just put, it's logical. And I'm like, well, I mean, if it's logical, you got less to say a lot of times. If you remember the pet expense one I just did, I did one right here. When someone owns 0 pets, we expect them to spend $342.6 on average. That might be logical because they might be spending money on their friends' pets, their family's pets. They might not call ownership of their pets, but it might also be illogical because it doesn't make sense someone would spend money. Good job, Lane, right there. It might not be logical because someone spending money on pets should probably own pets. And then for each additional pet, we expect someone's pet expense to increase by $254.2. That is the predicted increase in pet expense. The other model right here, for each additional year someone is older, we expect high school GPA to be lower by 0.11 on average. Throw a little on average in there. Especially yesterday, we went over the interpretations and gave the fill in the blanks. 8.6% of the variation in someone's high school GPA is explained by their age. It's an interpretation of R squared right there. And we could make a residual plot. This one's pretty good. What do you think is... This is pretty good. I really don't see any big issues with this one. Really, maybe mild outliers. There might be mild outliers right here, like a mild outlier. And I don't really know if there's big plot thickening. You want to really go for the big things right here if you look at a plot. You don't want to overanalyze it. You want to say, okay, is it mainly about the same thickness? Mild plot thickening, let's say. Mild plot thickening. But there's also more data there, so more data equals more spread. So possibly mild plot thickening. Is the linear model doing great? To see if the linear model is doing great, you want to see if it's about even scatter above and below. And so we're looking to see if the line cuts through the middle of the data. And if you look, the line is cutting through the middle. We're not caring how if it's like going the same distance out each time. We're caring if this goes up the same as this goes down, because you can have instances of nonlinear models where the data, and I'll show you one right here. Got a very famous one I use a lot for nonlinear models. Let's go here to data survey 10 and M save into LM height weight. We're using a little R now. So this is a non-linear model right here. And the reason it's non-linear is, especially over here at the end of the data, if you think the line should cut through the middle, what do you notice right over here? This is the big evidence of non-linearity at the end of it. What do you notice right there? Remember how I said the line should be cutting through the middle of the data? What do you notice in that yellow space? The line should cut through the middle of the data. There are no points above the line. So we have really easy ways to check this. One, we can do a higher order polynomial, and you can see the higher order polynomial actually starts to bend. These are ways we don't do into a 1, but we can see that it would like to bend because here's the model not bending, and it can't go through the middle of those points. And if we allow it to bend, it will bend. We can also see if we should be doing this with a check regression right here, which asks us if we should be using the linear model. And the answer is no, the linear model is a bad idea because we reject the linearity. So this is actually the lack of fit test you're seeing in JUMP right there. And this is a way we can check it. We can also check the equal spread, which is plot thickening, and normality of residuals. This model actually has a lot of problems, and there is a normal probability plot which doesn't follow the line. So we have evidence of non-normality of residuals. We have evidence of non-equal spread. We have evidence of non-linearity. So this model has a lot of problems. And that's how we would check it like in another class right there in 320 to be like, okay, it's got a bunch of problems, which are the conditions we usually check. QQ, it has to be 2 quantitative variables if we're doing regression. What are you thinking, Jesse? I like showing a little higher order stuff here just to show we have ways of analyzing, should we be fitting a nonlinear model? And this is the R squared adjusted I mentioned, which is the R squared for the multiple world. R squared adjusted also increased, and Akaike's information criteria, the corrected version, has decreased, which is how close we are to the truth. So whenever you make output, you should always be able to interpret and understand what this output means. Like this is for the second order polynomial, the parabola. We look at a corrected version of R squared. Yay! And R squared is how much we're explaining, right? So you want your R squared to be what, Jesse? If R squared, let's go in the basic sense, is how much we are explaining, you want your R squared to be what? You want your R squared to be what? If it's how much we are explaining. You'd want your R squared to be as high as possible. Like we want a really high R squared. But here's a problem we run into in multiple regression. If I allow this line to bend more, it'll go through more points. So why don't I just allow the line to bend a ridiculous amount? Like I can make the line squiggle, squiggle, squiggle as much as I want. Can I go up to 20th degree polynomials? I can. So now the line is bending a ridiculous amount, and we allowed it to go up to a 20 degree polynomial. But the issue is, if we allow it to bend this much, aren't we kind of cheating? So what R squared adjusted does is it's adjusted and gives us a penalty. So R squared adjusted is R squared penalized for how many things we're adding to the model. And there's a lot of ways to look at this, but quickly with Akaike, we would go to the 4th degree polynomial. R squared adjusted also kind of levels out on that. Lower Akaike criterion is better. So you just look for the lowest right here, and that's the answer. Like we should go to the 4th order polynomial. So if we go to just the 4th order, it's going to look kind of like this, where it gets the extra squiggle, the blue line right there. I wouldn't go up to a 20th degree. That's pretty crazy. And Akaike says that's a bad idea because his criteria is going higher. R squared adjusted is increasing a little bit, but it's all leveling out around this one. If you notice, there's no major increase. But that's what we do with upper level statistics. You have to be careful though. I could talk about holdout and validation subsets, but this is the basics and the backbone of what we do. It's a lot of fun, and we can find answers pretty quickly, and we can do the same things in jump. If you're like, wait a minute, but we're using jump, Brian. Well, let's go here to the fit the polynomial and just fit a bendy line. There you go. What other questions are there? We did a little bit of advanced to end right here. I love doing the advanced stuff, though. It's like, I don't know, it's fun. What other questions are there? I feel like there's not enough assignments out right now. Maybe I'll call them 320 right here, because we were doing some 320 output. My phone's case is breaking. The thing on the bottom is like hanging on by a thread. I shouldn't mess with it. I don't even know how that happened. My beautiful purple case. My wife got what did she do? She didn't like this case. And now this case is falling apart. So she got a new case. Maybe I should do that too, because this case is falling apart on me. Let's see. 320. I'm going to announce to them, like, currently doing office hours. Swing by with questions. Let's see. Okay. Okay. Chapter 7, Manager Bookstore. Yeah, let's do it. Is that the homework or the quiz? It's the quiz. Okay, well, if 320 comes by, they're going to have to... Is this the workers and the sales one? I think this is the workers and the sales. Gonna get it going right here. Let's take a look. Chapter 7 quiz. A lot of questions here. Quiz. Okay. Manager at the bookstore. Oh, we just found it. Well, I'll be. New York City? Yeah, and drop these questions anytime. I'm gone right now. Okay. 36, 13. Can't wait to get my new contacts. Chapter 7 quiz. Okay, there's the first one. and the New York City data. Okay. And Schedule 1, Chapter 7 quiz. Got it. All right, let's do the first one right here. Here we go. So I highly suggest using the regression solver or using jump to solve these. So if we take a look, and I'll probably use, why are they putting the coefficients down here? I'll probably use jump to solve this. I do like using jump, and the output's just nice and neat. We're gonna go right here to copy the data, and we copy the data to the clipboard. And once you do this, you need to hit Control-C or Command-C to copy it. Or you could probably click right here and go to copy. Many ways, make sure it's copied. Now that you have the data copied, we're gonna go over to jump. And I have jump open. I have a bunch of things open in jump. So inside of jump, we're going to go to File, New, Data Table. File, New, Data Table. Under File, New, Data Table, you will get a new data table, and don't click inside of it yet. A lot of people do that. Go here to Edit, and then Paste with Column Names. Edit, Paste with Column Names. There you go. Now, what do you want to see over here? That means you've done it correctly. And restart if you don't see this. What do you want to see over here? If you don't see this, restart, because you've probably done something wrong on the pasting. And it happens many times to many people. What do you want to see over here? Both blue, exactly. If they're not both blue, it's quite possible that when you pasted, you didn't paste with column names, and then you tried to correct it, and maybe you did correct it. So try restarting, paste with column names, very important right there. So make sure they are both blue, both quantitative, very important, or you will not get the right analysis. So find the slope. Did they give us the slope? They didn't, but you could solve for it. We won't have you solve those equations. We're going to go back here to the data set, and we want to predict sales. So let's go here to Analyze, Fit Y by X. Analyze, Fit Y by X. Once we go to Analyze, Fit Y by X, we are going to predict sales. That is the response we care about, with explaining it by the number of people working. So we put the X variable, number of workers, explains the sales in thousands of dollars, and let's click OK. If you notice, more people working is associated with higher sales. So we get the scatter plot right here. And with this, we're going to click the red arrow and go to Fit Line. So once we fit the line, it will give us the regression equation. So let's go ahead and fit the line, and there is the line. Now, this is a lot of output, but we have to know what we're looking at. So let's clean this up a little bit here. That's the sales in thousands of dollars. And then this right here is the number of workers. A little easier to look at. We can just call this workers. You don't have to make these changes, but it just makes more sense. And here's the sales. And it's in thousands. We'll remember that right there. So now we have that the sales is equal to 8.78 plus 0.913 times workers, and the coefficients are also down here for the estimate of the intercept and the estimate of the coefficient of the slope. What does it want? It wants B1, which is the estimate of the slope right here, which is 0.913. And it says round to 3 decimals, so 0.914. There we go. What does B1 mean in this context? So here's what you want to do. If you are practicing for the test, what do you think you should do, Jesse? Don't read their answers. If you are practicing for the test, what should you do? So what should you do if you're practicing for the test? So I fear like so few people are going to do this, but if you do this, you will start to learn this, you will get it down, and when you get to the test and you have to interpret these, you'll be able to do it. So what you want to do right now is go to your notes from class where we have the interpretations. For each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. Write it down and then find the answer that matches. So what we want to do right here, great job, Jesse, right there, we'll throw you some points, is we want to interpret the coefficient of the slope right here. For each additional worker, we expect the sales in thousands of dollars to increase by 0.91 on average. So for each additional X, we expect Y to increase by B1 on average. So I'm highlighting it. Please write it down as we say it right here. For each additional X, we expect Y to increase, because it's positive right here, by B1 on average. So for each additional worker, we expect the sales in thousands of dollars to increase by 0.91 on average. It means that on average, an increase of, it means on average, the number of salespeople working, no. It means on average, the total, no. it means that on average, an additional increase in sales is associated with each person working. That is correct. Now the intercept right here, let's go grab the intercept value. The intercept value is this. Let's delete it down. 3 decimal places right there. The value of the intercept means, what does B0 mean in context? It means that on average, so when X is equal to 0, we expect Y to equal B0. So it means that on average, the expected sales with 0 people working, when 0 people are working, we expect sales to be this on average. It does not make sense because it is unlikely that any sales will be made with 0 salespeople working. Write the regression equation right here. So we're literally just going to take these values. Oh, they said to 3 decimals. Dun, dun, dun. So that's a 2 right there. And to 3 decimals. And to 3 decimals. If 20 people are working, how do you think we would solve for 20 people working right here, Jesse? What do you think we would do with this to solve for 20 people working? If 20 people are working, what should we do with this equation? How would we solve it? If 20 people are working, what would we do right here? So remember, people plug 20 in, exactly. So we're just going to take right here, plug 20 into X, and this is now the what sales for 20 people working. This is now the what sales for 20 people working. That is now the what sales for 20 people working. You would call this the what sales for 20 people working. Round to the nearest $10. Oh, because it's in thousands of dollars. There you go. And then it says round to the nearest $10. Predicted sales. And if you notice they have a hat over it, the hat means predicted. Very important right there to say that this is predicted sales. It says round to the nearest $10, so make sure to round this to 27060. So 27060. Now that we have the predicted sales, it says to us now, if there are actually this many sales, well, so then this right here is the Y hat, because we just solved it from here. So what is actual sales in notation? If the sales were actually this, what are the actual sales in notation? And it would look something like this now. That point would be here. So what is the notation for the actual sales? It says the actual sales are that. So what is the notation for that? It says the actual sales are 28,000. What is the notation for that? Be careful. Unless I've done it wrong. But what is the notation for the actual sales? Like if the sales are actually that, that would be the value of what? If the sales are actually that, that is the value of what? You're on the right track right there, Jesse. So what is this in notation right here? The actual sales would be the value of what? And we said X equals 20. So the actual sales in notation is the value of Y. So we then take and plug into the equation residual equals actual minus predicted, where E is residual. Does that make sense, all the notation I've drawn on here? So residual of 940 is found by 2800 actual minus the predicted of 27060. Yep, so that makes sense right there. And then it's above the predicted right there. You see right there. So that's a positive residual. So when the residuals are positive, the actual is above the predicted. So it is a positive residual. And those are key things to notice. So now you have to be careful. Did we under or overestimate it? Did we under or overestimate it? The prediction under or overestimated it? The prediction under or overestimated it? So make sure to look at the plot right there. Did it under or overestimate it? Because remember, the line makes the predictions. So the prediction was a what? Yep, Jesse, great job right there. We underestimated it. Exactly. We underestimated it because the line's underneath it. Yeah, great. This is, sometimes, I'm mean to my Pearson, which I shouldn't be. It's what we use. So I gotta champion it. But really, this is a question that covers pretty much everything we covered yesterday. It went through residuals. Like if you go through and solve the equations, it has some decent interpretations. I wish it had to write them out, but then we'd have to grade them manually. So it is automated on the grading of some of these. But the interpretations are pretty good. It has you find the coefficients. But knowing what you're seeing right there is key. So really good question. So great work. That's a really good one. The New York City data. Here's a different manager. We could do this one really quick. The manager at a bookstore. Here's the other manager of a bookstore one. View the data. We got an R squared right here. All right, so here's the R squared right here. Let's go ahead and square it. And there's correlation, 0.974 times itself is R squared. So now we times it by, does it want it to do times 100? Yeah, it is. Okay, good. R squared is always, or I always report it as a percentage. So 94 point, and let's see, the value of R squared is, which is the percent of variation in number of sales that can be accounted for by the regression, is the percent of variation in the variance, percent of variance in the sales that can be accounted for by the number of sales. No. The R squared value is, which is the percent of variance in sales that can be accounted for the regression model of number of people working. That sounds right. Don't love these interpretations, but how many decimals does it want? To 1 decimal. There we go. And let me read the last one, which is the percent of variation in number of salespeople working. No, we're trying to explain sales. So that should be right there. Really? Where did I go wrong? The R squared value, which is the percent of variance in sales that can be accounted for by the regression. Oh, they're literally talking about the XY relationship right there. Really? Oh, that's very, very mathy. The change right here is, and let me just tell you how I would read this. So they're getting very, very mathy on that, on which way it's regressed. Regression of sales on number of salespeople working. So if you look at our model right here, it's sales regressed on workers. I missed that last part of the sentence. Very key right there to the way they want it interpreted. But once again, I would interpret this, at least for this model, 93.5% of the variation or 93.6% of the variation in sales is explained by workers, so the variation in workers. So 93.6% of the variation in sales is explained by the variation in workers. That's a lot of variation. That's a very good regression model. So once again, for your test, 93.6% of the variation in Y is explained by the variation in X. So 93.6% of the variation in sales is explained by the variation in workers. Very key right there to know how to do that and interpret the R squared. The last bit is a little bit mathy that we regress Y on X, but we prefer to say 94.9% of the variation in sales is explained by the variation in workers. So pretty good right there. We got another one right here. 2 more. Could we do the bursts? The table shows number burst. You bet, Jesse. Let me go find the next one and read the questions fully. Okay, wheels. Okay. We have the New York City data. The New York City data. Tell me if you see the table one. Well, those are easy ones. Oh, residual plots. I like those. Those are fun. The New York City. Okay, I think this is the one they wanted. So the question was, let me timestamp it. The New York City data. Cool. Okay, so 5033. Okay. The New York City Data Initiative reports on annual water consumption. The accompanying table shows daily water consumption per capita in gallons from 1986 to 2019, along with a scatter plot, technically a time plot then. Where's the scatter plot? Yep, it's time plot. Look at the end of this. What do you immediately notice at the end of this, Jesse? I haven't read the full question yet, but I see something that's a bit of an issue immediately with this. It's not really this right here. It's that at the end. So what do we immediately see right here? Really noticing this in the where they're probably going to go with this, I assume, because that's a major issue I see. So what issue do we see with this that I would probably take note of immediately? And this is what you want to be able to do. Don't read their questions. Curves at the end, exactly. So we have a problem with straight enough right here. Like if we go through it, at the end, the line would not be going straight through it. So we probably have a bit of nonlinearity. What are the variables in the regression? Water consumption in million of gallons per person. Like what's the X and the Y? What are the units of the slope? Oh gosh, very, very mathy. Oh, they're not even going to get into the nonlinear relationship? Okay. But they are going to have you solve for correlation, which is a good find right here. So it's going to be the units of slope is for each additional year. So millions of gallons per person per year. That sounds right there, because for each year, the millions of gallon difference. So for each additional year, we expect millions of gallons in water consumption to decrease by this amount. But here's where they're trying to trick you. And do they give you, well, they give you R squared. So I'm going to pause right here. What is the correlation? You can see the R squared right there. See if you can find it yourself. I'll give you a moment. But this is a question we definitely, people get wrong on the test all the time. What is the correlation? So correlation is R, and this is R squared. But this is a very commonly missed question right here. So there's R squared. What is R for correlation? Very commonly missed question. Because correlation takes into account direction. That's a hint right there. Correlation also takes into account direction. Well, okay, so let's do that. Let's check it out. You ready? So we take R squared and put it as a decimal and square root it. Is that correlation? Is that the correlation? That is a correlation of 0.933. Is that the correlation of this plot right here? It has a correlation of 0.9633. Is it? And it'd be negative. Great job, Jesse, right there. That's right. So it's negative. You always check the direction when you square root it, because square root is technically plus or minus. So be careful. You have to check the direction after square rooting. We should get 100. Yes. So that's the maybe harder part. That's a really good question down here. I wish they had you interpret it, but they do want you to know for each additional year, we expect the decrease in water millions of gallons to be this on average. They want you to know the XY variables. Decent question, but the real good one is right here. We put stuff like that on the test. So I'm always going to point to what I've seen on the test, and I've definitely seen this on the test where people forget that it's negative, and you have to look at it or look at the slope. The table shows. Let's see if we can find the table shows. Here we are with the table shows. And we're out of questions after this, so keep asking those questions. Remember, if you're watching this in the future, then swing by office hours and ask some questions that you're stuck on. We can work them and explain how to do them. So we see here 2 quantitative variables, and we're looking at the years since 1900 and the birth rate. Now, you can actually deduce, that's the word of the day, the right answer right here. Take a look. This shows positive, this shows negative, this shows random, this shows positive and negative. So if you start going right here on the table, the years since 1900, and this one does have a trick at the end because we'll have to do some interesting math here later on. If you start going through here, you'll notice that the birth rate is declining. 19, 18, 14, 15, 15, 16, 14, 14, 14, 12, 12. So this one has the high value in the middle, as does this one. The high value is here at the start. So the only one that has the high value at the start is this, where 19's at the start. Hey, Will, good to see you here. So that is the right answer. We are going to have to do some of the mathematics here. So let's go ahead and solve this in Jump. And this one's a bit tricky because the way the plot is it says years since 1900. So we're going to copy the data. We're going to hit Control-C or Command-C on a Mac or copy. Now we're going to go over here to Jump, and we're going to go to File, New, Data Table. File, New, Data Table. I think I can. What are you wondering about, Will? Ask away. I might be able to do it. Remember to fill out the form if you want any possible regrades, but ask away. So we're going to go to Edit, Paste with Column Names. Edit, Paste with Column Names. Make sure to do that. Make sure they're both blue. Now, there's a few ways to do this. Years since 1900. You can just type them in. It's probably the best way. Don't make any errors, though. There is another way, which I guess I'll show in a second. But don't make any errors. This is how it's done, and this is the hard part of the question, probably. It doesn't use that. There's another way right here where if we go to years since, you could do the following. You can do what's called a formula right here. It's another way of doing it. Click the year variable and then do minus 1900. So now you click there, apply OK, and it'll do it for you. So that is a formula column right there using the year, or you could do it yourself. You just have to get the variable looking this way, as The Rock would say.
It doesn't matter.
Doesn't matter which way you do it. You just have to get, here we'll move the formula to. Oh, and then it actually just saved those values probably. You have to get this right here. So make sure you get your data looking this way. So now that we have it looking this way, we can go to the analyze, fit y by x, or you can just literally enter in the values if you want. Analyze fit y by x, and go right here, years since 1900, and then the rate right here. And we will also see the scatter plot that we just saw a moment ago. Probably, which one? Well, there's a few of those, Will. Let me know, and I'll kind of do some examples of those. Kind of tell me the gist of the problem, and I can do examples based on those. There's a lot of, so I can come up with some examples. And this is the plot we saw earlier with the downward trend, a little bit of weirdness here in the middle where things don't necessarily follow it. Let's go here to the top red arrow and go to fit line. When we fit the line, it'll give the regression equation right here. So here's the regression equation with the intercept, and here's the regression equation with the slope. And here is the x variable of interest and the y response variable right there. So let's go back and see what it says. Describe the trend. It's been decreasing over time, very clearly. Find the regression equation. So we need to take our regression equation that we have right over here, and we're just literally going to copy paste. Now, one key thing to know is that this is negative. This is a negative relationship. I go 2 decimal places. There we go. Check to see if there's an appropriate model. Ooh. Yeah, do it right here. So, so to see if the model is appropriate, yes, because it's reasonably straight and there are no outliers. Possibly. Oh, well, the data is quantitative. I think it's mostly linear. Yes, because the scatter plot shows that there are no lurking variables or variables outside the XY relationship. No, because the scatter plot shows evidence of outliers. This one I'm a little bit concerned on because these are always iffy, the interpretation ones. So wait till we finish this. Those aren't big outliers, and that isn't big nonlinearity. Like overall, like that one had nonlinearity at the end. It's reasonably straight right here, reasonably good. I would say reasonably straight, reasonably good. Awesome, Jesse. Yep. You're welcome, Jesse. So we'll see if we get this one right. I would say reasonably good right here. Yes, because the scatter plot is reasonably straight and there are no big outliers. Interpret the slope for each additional year since 1900. It's the slope is the number of births per year since 1900. The number, 1965. For each additional birth, no. Number of births per year has been changing by an amount equal to the slope per year on average. This right here talks about the 1900. The table gives rates only at intervals. Estimate what it would be in 1978. So we have to turn 1978 into 78 and solve it through the equation. It's kind of a key part to this right here is that when you're solving it, you have to realize that you're plugging in years since 1900. So this needs to be 78 for this when we plug it into the equation. So let's go ahead and take 78 and just plug it in right there. So we're going to go right here, type 78, times it by 0.11, which is the rounded to 2 decimals version. And then we're going to take 225.67 and minus from it this right here, 17.09. There we go, round to 1 decimal place. That should be correct. In 1978, there was actually 15 births right there per so many thousand population. So what was the residual? So think about this. This is the predicted amount, or actually, we should have just kept that model up. So all in 1978, actually 15. So the model in 1978, let's say, which would be about here, 5, 7. We actually saw something down here, and we were up here. So we are below the model. We are below the model. and we're below the model. I think we said 17.1 is what the model predicts, and this is at 15, it's saying. So the distance below the model is negative 2.1. Remember, it's residual equals the actual minus the predicted. We just found the predicted value of 17.1, and the actual value is 15, making the residual negative 2.1 right there. So negative 2.1. There we go. So the model predicted this many more births. So remember, we are above it, so the residual is negative. It predicted 2.1 more births per thousand. Gotta be careful. You see, the units here is the hard part because they're talking about in thousands. I think they are keeping to the same units, but 2.1. The birth rate in 2020, which is way in the future, well, it's past now, it would be at 120, because remember, we're subtracting off 1900 from it. So they want us to go back to the model again and simply input the value of 120 right here. So we're just going to go and input 120 times by 0.11, and then subtract that from 25.67, and we get the value of 12.47. And so this is the value right here to one decimal. Come on if you think this is on their faith on this prediction. There is a great deal of faith in this prediction because the X value is large. No. There's no faith because it's an extrapolation that's far beyond the data. No. There's some faith in the predicted value because this is not a very large extrapolation. So what they're pointing to right here is you're predicting basically where this will go next. Extrapolation is when you leave the X bounds of your model. So extrapolating would happen if we were to predict on years before 1960 or years after 2015. At this point, you are leaving the X bounds of your model right here. So we call that an extrapolation. You're not extrapolating within the model. You're extrapolating outside the X bounds. So you do it over here, and you do it on the outside of where the model ends. So specifically in these regions that I'm highlighting is where we don't have data, and the model would have to extrapolate to make predictions. So that would be an extrapolation of the model. It's a mild extrapolation, so we might have some faith. The more you extrapolate, the worse it gets. And here's a big extrapolation. Once again, we're going to take the value of 150 because this is 150 years past 1900 and simply plug in 150 right here. So let's plug in 150. And there we go. 25.67. And there's the answer. 9.2 is it rounded to one decimal? And I would say there is no faith in this prediction because extrapolating that far beyond the data is dangerous, and that appears to be accurate. Did we get everything? Oh my gosh. What was the one we were questioning on? Is it really that? No. Is it this one? Oh, that's not the answer either which way. Is it nonlinear? No way. Okay, so we got that one. Which one did I misenter? Oh, is this one? Oh, really? The number of bursts per year has been changing by the amount. Really? Wow. I don't like their interpretation of the slope when they do it that way. So sorry about that one right there that we missed. The number of bursts per year per 1,000 population has been changing by an amount equal to the slope per year on average. Yeah, but they really need to mention, it is for each additional year. It's not in units of 5. But once again, I would preferably just interpret this myself rather than read their interpretation. So I'd say for each additional year since 1900, we expect the birth rate to decrease by 0.11 in thousands of births, 0.11 per 1,000 individuals a year. So for each additional year since 1900, we expect the birth rate to decrease by 0.11 on average, and that would be good right there. So make sure to know how to interpret these coefficients. You will be asked to write them out on the test. This right here is the predicted value for 1900 because when x is equal to 0, there'd be 0 years since 1900. So when x is equal to 0, there we would have a prediction of 25.67 for the birth rate. Good stuff right there. So Will, to your question right here, contingency tables. Let's take a look at contingency tables on test 1. Set to a 1. Oh, hey, let's take a look at that. When we have a contingency table, we have 2 categorical variables. So let's see this question right here and see how to answer it. We would go right here, and I think I labeled the time, right? I did. Okay. So let's say the following question. What percent of people have broken a bone of the males? What percent of people have broken a bone of the males? So what percent of people have broken a bone of the males? So what percent of people, have broken a bone of the males? So what would that be right there, Will? What percent of people have broken a bone of the males? How would we find that mathematically? There's a really good, sometimes My Pearson really does a great job, and there's a great My Pearson question that goes over the small, subtle differences in wording, because this is a conditional distribution. So what percent of people have broken a bone of the males? We'll see. We'll give it a moment more right here. What percent of people have broken a bone of the males? So we'd go right here. We'd have to look of the males. Is it? Let's find out. There you go. Oh, it's 54.6%. Then there's different things like what percent of people have broken a bone and are male? What percent of males have broken? But there's many ways to say it. I could say, given someone is male, what's the probability they've broken a bone? If an individual is male, what is the probability they've broken a bone? Of the people who are male, what is the probability they've broken a bone? Of all people, this is a different thing. Is in probability decimal and not a percentage. Depends on, and so definitely if you think it was a error, fill out the form. I sent out a form today if there was an issue with the way you think it was answered. But all these right here could mean slightly different things. Like, what is the probability? What percent of people have broken a bone of the males? So that is going to be, we're going to highlight the ones that are similar to it. That would come to the same conclusion. This, if an individual is male. This, of the people who are male. This, given someone is male. What percent of people have broken a bone? And oops, nope, didn't want to change color right there is what I wanted to do. So these are actually different right here, these two. So these two would have the answer if you were to take and divide out of the total. So these two you would need to use the total for and do the following. So those would have the answer 194 over 806. So probability can be expressed as a percentage or can be expressed as a decimal, like the proportion of people, but still can be expressed like a probability there. But if you feel like it was the way the answer was put in, just let me know on that via the form. But does that make sense right there, Will? What percent of people have broken a bone of the males? So that's saying only of the males. So only of the males, what percent of them have broken a bone of the males? You could do the following too. Think about this. If we had a table right here, what percent of students choose to live on campus of the in-state students? What percent of students choose to live on campus of the in-state students? So if we had a table right here, and we drew it, and we go here to in or out of state, in or out, on or off, and we usually put them on the other sides. Ooh. So in, out, or in or off, or on or off, my gosh. On or off campus, in state, out of state. And let's say here 100 here, 100 here, nice numbers, 200, Let's go in-state 120, out-of-state 80, and then 80, 40, and then this has to be 60, 20. Okay, so what percent of students choose to live on campus of the in-state students? What percent of students choose to live on campus of the in-state students? What would this be here, Will? So how would we solve this one? What percent of students choose to live on campus of the in-state students? What would the answer be to this one? Well, but it's a percent though. So what percent of students choose to live on state of the in-state? And so show me the math you're doing right there, Will. So you could answer, and if you feel like it's the way the answer was put in, let me know. Like if it was a decimal issue, fill out the form and I can check. I'm going to be doing all that this weekend, updating grades. If people say, wait a minute, I entered it this way and there was a miscommunication. So show me the math you did right there. So what percent of students choose to live on campus of the in-state students? Yep, 67. Yep, 66.66. Yep. So it'd be of the in-state. There we go, right there. So there's the numbers, and that's the conditional distribution. Does that make sense right there, Will? And good job right there. These, it can be tricky sometimes, but that's the conditional distribution right there. Yep. And so probably a lot of people have asked about the dark chocolate one because it's like you're looking at conditionally, like what percent of the people who had extreme dark chocolate disliked it. So it's like given someone had, and there's lots of ways to say it, and that's the issue. And that's why I try during class to give as many versions of it as I can. Once again, we don't know how someone will talk to you in the world, so we try to give multiple examples and multiple versions because someone could say it many different ways, but then there are ways that are different, like what percent of people have broken a bone and are male is different from what percent of people have broken a bone of the males. So this right here would be out of everybody, like what percent of people are this and this, what percent of people are this of the this. So the subtle difference right here of the versus and are. But very important right there, big differences. I thought it would have asked what percent of dark chocolate tasters said dislike if they wanted to know that. Well, it's another way of phrasing it. So it could say what percent of this group. So, but the of this group is very important right there. But there's many, many ways to say it. So we've got all these yellow ways right here would come to the same conclusion. Like, given someone is male, what's the probability they've broken a bone? If an individual is male, what's the probability they've broken a bone? Of the people who are male, what's the probability they've broken a bone? I took it as a what percent of tasters, as in all tasters. But the of is key right here. So we could say what percent of people. You see how this says what percent of people? So it is saying of all people. So it is true we're looking at all people, but the of the males is key right here because it's saying what percent of people, and it could say who meet the criteria male. So that's another way of phrasing it. What percent of people who meet the criteria male have broken a bone. So this is another synonymous way of saying it right here. You have to be, so what we try to do, yeah. And so this tough one, Will, especially because there's many, many ways to say it. So sometimes the test, I try to throw as much wording as I can in class and do as many different versions to then hopefully prepare people for the test. Because I can't like only do one wording, because then what if you go out and you try to use the knowledge and you're like, well, Brian never said it this way. I want to make sure we see many, many ways to say it. So I'll usually come up with, I think we were doing that during the, we did the Titanic data in class, right? And then I asked people to write some conditional questions. So that's what I usually do in class is to say, come up with your own conditional question. And so I try to have people in the chat, no worries, Will. I try to have people in the chat come up with their own ways of phrasing it to show that there's multiple ways. So my goal is like, not that we only learn one structured way of saying it, is that we think about multiple ways we could narrow it down to a conditional distribution. And it's tough because like we've already come up with 1, 2, 3, 4, 5 ways to come to the same conclusion. It'd be nice if everything was exactly the same every time we did every question, but that's why even on my Pearson, it has different ways of phrasing it to be like, well, what if we said it this way? Would it mean the same thing? So you always want to think about like, what exactly are they asking? Is it like, is it exactly? But yeah, so good questions, Will. We'll see. Has Has Discord messaged me? No, I haven't messaged yet. Well, let's see. Let me see. I wish I could unmark a message. I just clicked a message and I want to go back and view this message later. Well, we'll head over here. Might end office hours a little bit early today. I think everyone's tired from the week. It was a big week this week. But good times. Any other questions as we get going? I know, right? I think mine is too. But yeah. Well, I'm gonna take a quick break right here, and then we'll be back. Well, good luck. You had an anatomy exam the day after stats exam. Oh my gosh. Well, until then, we'll be back here doing class in a little bit. Until then, bye for now, everyone. Bye.